Alright, so in this lecture, I'm gonna be talking about a very important and classic paper about contrastive learning, and it is unsupervised learning because it's one of the first classic articles about contrastive learning. This article by Jeffrey Hinton in 2020. So this paper presents SimCLR, which is a simple framework for contrastive learning of visual representations. We simplify recently proposed contrastive self-supervised learning algorithms without requiring specialized architectures or a memory bank. Because this memory bank, this has a problem, so we don't even use this. So in order to understand what enables the contrastive prediction tasks to learn useful representations, we systematically study the major components of our framework. We show that composition of data augmentations plays a critical role in defining effective predictive tasks, introducing a learnable nonlinear transformation between the representations and the contrastive loss substantially improves the quality of the learned representations. And finally, they showed that contrastive learning benefits from large batch sizes. For example, if you go from 128 to 256, you see an improvement. Or even if you increase more training, more epochs, then you see still the loss is going down, accuracy is going high for both training and validation at the same time. And so it keeps improving if you increase the epochs. So it's a very good, interesting benefit. So they showed that composition of multiple data augmentation operations is crucial in defining contrastive prediction tasks that yield effective representations. In addition, unsupervised contrastive learning benefits from stronger data augmentation than supervised learning. Introducing a learnable nonlinear transformation between the representation and the contrastive loss substantially improves the quality of the learned representations. And representation learning with contrastive cross-entropy loss benefits from normalized embeddings and an appropriately adjusted temperature parameter. Contrastive learning benefits from, as I said, larger batch sizes and larger epochs compared to its supervised counterpart. Like supervised learning, contrastive learning benefits from deeper and wider networks. So this is the architecture. Like before, we do augmentations, but we do one more nonlinear transformation here, and we maximize the agreement. But a stochastic, it has major components. For example, a stochastic data augmentation, a neural base encoder that extracts representation from augmented data examples. For example, they use ResNet to obtain that F that I told you. So, but it has also a small network projection head, because they say that it maps the representation to the space where contrastive law is applied, and they use a multi-layer perceptron with one hidden layer to obtain Z, and Z here is a ReLU activation, which is a nonlinear activation function, and a contrastive loss function defining finally for contrastive prediction task. So we have positive pair which aims to identify X tilde. And we randomly sample a mini batch of n examples and define the contrastive prediction task on pairs of augmented examples derived from the mini batch, resulting in 2n data points. We do not sample negative examples explicitly. Instead, given a positive pair, so this is an augmentation of this image X, So instead, given a positive pair, we treat the other two n-1 augmented example within a mini batch as negative examples, because we have other images as well that themselves have augmentation. So if you go from here to here or from here to here, all of these are negative. But of course, these are positive. These are positive because they are augmentation. They are the similar images because it's just rotation and something. And so the loss can be written as this. And this one here is always indicator function evaluating to 1. And this is the full algorithm. So first you do representation and then projection. Until here your representation, and then to project it to even smaller space, and then you maximize the agreement. So quite simple, quite powerful. It is called SimCLR. But you can keep train with large batch size and you see even greater improvement. So a batch size of 8,000 gives us 1,000 negative examples. Such a big batch size. Of course, you need more RAM, and I only use one GPU, and my RAM is not enough, so I should increase my GPU. Because the bigger your batch size, the more you have problems with RAM and many other things. So global BN. Standard ResNets use batch normalization in distributed training with data parallelism. The BN, mean and variance are typically aggregated locally per device. And you see global and local views. Solid rectangles are images. Dashed rectangles are random crops. You crop an image very randomly. And most of our study, some additional pre-training C410 can be found. And then for default, we use a ResNet, as I said, ResNet 50. And what else? So these are crop and size, different kinds of augmentation, crop and resize, color and distort, many different augmentation, cutout. But unfortunately, in natural language processing, you have very limited ways, and those are naive approaches because the problem is significantly more difficult. And it's different. It's not just like an image that you can rotate it and everything looks nice. And they also did this second transformation, which linear evaluation under individual composition of data augmentations. And as I said, a nonlinear projection head improves the representation quality of the layer before it. So we then studied the importance of including a projection head, this G. And this figure shows linear evaluation result using 3 different architectures: identity mapping, linear projection, and the default nonlinear projection with one additional hidden layer. So as I said, we can use random crop, for example, resizing it to this, or color distortion. All of them are data augmentations. But we can increase the number. So you increase the number of batch sizes. So we start from 256 and we go to until 8,192. And also, if your number of epochs starts from 100, increasing it double, and then 800.